Okay, so hi, this is Ayush, and today we are going to discuss find the first and last position of element in sorted array. So let's read the problem. Given an array of integer nums sorted in non-decreasing order, find the starting and ending point of position of given target value. If target is not found in array, return -1 and -1. We must write an algorithm in O of log and complex runtime complexity. So this question was asked in these many companies, as you can see on the screen. So this is also an important question in terms of interview. So let's discuss it. What does question mean and what should we do? So here we are. Okay, so in this example, as you can see, we have this array, right? 5 7 7 8 8 8 and 10. We have repeated occurrences of elements. We have a target, we have to find 8, right? So we have to find the first position of 8 and the last position of 8. As you can see, I have highlighted those positions. This is the first position of 8 in our array, right? This is the first position and this is the last position of 8. We have to find these positions using binary search. If this question comes up in an interview, what you would do is first explain the brute force approach using linear search, right? What would be that brute force approach? You would simply traverse the array. You'll look through each element like this, 7 8 and 8 here. You find the 8, right? Once you find the 8, you'll store this in first position index, and then you move on and move on. You will when you find the last position, you'll keep updating your last position of 8. I'll just quickly show you what would be the brute force. Let's say this was your, let's call it FPOS for first position and LPOS for last position, right? So initially my first and last position would be -1. I'm doing a linear search here. I would traverse through index. Let's write the index itself: 0 1 2 3 4 5 and 6, right? I would traverse through indexes. I will traverse through 0. I'll check, is it equal to target? No. 5 is not equal to 8. And I'll check here, is it equal to target? No. Now is it equal to target? No. Now it is equal. Now 8 is equal to target. It is at index 3. Now I would update my first position and last position to be 3, right? Now I would move on. I can see that this at number at index 4 is also equal to target. Then what I'll do, I will not update the first position now, because first position is already updated and it must be updated only once, right? After -1, we have already found the first position. We don't need to change it. So we found the 8 again. So what I'll do is just update my last position to be 4, and we will move on. This is like I'm at index 5 and I have found target again. So what I'll do is update my last position again. I would not change the first position. Update my last position to be 5, and at last we are at 6. We are at the end of the array. We don't this is not matching to target, and at last we are at end. So yeah, this would be our final answer, 3 and 5, which makes sense. But this approach, I have told you just now, is basically O of n, which is not the quite optimal solution in an interview. Why? Because it is given that our array is sorted. If this was an unsorted array, then this approach is the only way to do, right? But as this is sorted, you should get the hint of binary search here. If array is sorted, you should get the hint of binary search, and you can optimize this code to like log n complexity, as we discussed, so that it runs it is interviewer will be happy. Okay, we can optimize this code. So let's discuss the optimal approach now. Let's erase this. Right, we have to find the target. What as you can notice, one thing is that we have to find these two indexes, the first and last occurrences, right? So to find two indexes, we need to find basically two targets, right? Two positional targets, right? So for each target I need to perform a binary search, right? So for each target to perform, like for first position I need to perform one binary search, and for finding the last position of the target I need to perform another binary search. As you have noticed the pattern by now, you should for binary search to like execute properly, you can only find one specific target using binary search. For finding another target, you need to apply another binary search, because you would keep eliminating halves. You might have eliminated the half. In linear search, as we did in brute force, you were like able to like find the first and last position in one search itself. But in binary search, this is not the case. So first observation is that you need two searches, two binary search needed. And basically one would be for first position and second would be for last position. Pretty clear? So let's now our problem simplifies to this. We need to find first position using one binary search. We need to find last position using a second binary search. So let's try to find the first position now. Let's try to find how do we find the first position using binary search. We will come to last position later. So we will do simple. Let's write target here actually. Yeah, let's do a simple binary search as we discussed in our previous videos. So this is our low, this is our high, and this would be our mid. Got it? So I will now actually let's just write down low and high so we can keep track of it. Okay, so I'll check, is my mid equal to target? Yes. So I would initial low was this and high was 6. Okay, so I would update. I have found the mid, right? Now what should I do? You have already found the target, but do we return the target now? No, because in this question you don't have to return any index where you find the target. You have to return specifically the first index for this sub problem. Okay, so for this sub problem, what you would do now is, okay, I have found the target. I have found the target at mid, but there might exist something before this. The first occurrence might be before this as well, right? So if I find like here my target to be here, I can say, okay, this might be my first occurrence, but something before that can also be my first occurrence. So to find the first occurrence again, what I'll do is just search left. To search left, I would just move my high pointer here. Make sense? So what are we doing? Basically, let's write it down. We are finding the first index in this case. So if my nums of mid is basically greater than or equal to target, if we are also equal to target, then I would search left. Why so? Let's say for now, let's terminate this binary search. Let's say my mid was this somehow. Okay, for example, then we found the target, but still I need to search left to find the first occurrence. So I need to search left, right? Even if my mid was here, I need to search left anyways, right? I know 10 is like greater than my 10 is greater than my target. 10 is greater than target, greater than equal to target. So I need to search left. It must lie, as array is sorted, it must lie before. So let's erase this. So I need to search left. This is the whole point. Even if my mid was here, okay, I agree that this is equal to target, but can we find something better than it? Can we find something like more closer index to first occurrence? We cannot guarantee that this is first occurrence, right, until we like end the binary search. So I can say, yeah, this index 4 can be my first occurrence, but let's search more to the left to see, is there anything else? Is there one more 8 to left of it? Are there any more 8s to the left of it? So we'll search left. So this is the intuition we would use. So actually let's write these things down. So as I said, if mid was nums of mid is greater than equal to target, then I would search left, right? And if else, basically else means here nums of mid would be like a lesser than target. If it's strictly lesser than target, consider this. Mid is here. If it's lesser than target, 7 is lesser than 8, right? So simple binary search would do what? Search right. Simple. So I would search right. So let's do it here. As our low was this, high was this, mid was this. I saw that I'm equal to target now. So I'm equal to target. What I'll do, this condition holds. Now nums of mid is now greater than or equal to target. I found my occurrence, but I'm checking is there any more occurrence to the left. So I would search left now. So let's update our low and high pointers to search left. So low becomes 0 itself and high becomes 2 instead of 6. So now I would search, this would be my mid now. Is my mid equal to target now? No, mid is not equal to target. So as mid is basically lesser than target now. Okay, this condition holds. Mid is now lesser than target, so I'll search right. To search right, I'll update my low pointer to be mid plus 1. So low would come here, which is mid plus 1. It would become 2. So my low, high and mid are now equal. Is this equal to target? No. And is this lesser than or equal to target? Yes. This is like not, we don't have to, we have checked already equal to. We are seeing that now my nums of mid is lesser than target. So now as it is lesser than target, I need to search right. So to search right, what do? We just do a low equal to mid plus 1. So I'll just do low equal to mid plus 1, 3, and low would move here. So as you can see now this is interesting. Our binary search has terminated, and where does my low pointer lie? My low pointer lies at 8, the first occurrence. So my low pointer would store the answer. How this is happening and everything, you can just do dry run yourself. You would understand why this is happening, because this is all about search space. We have reduced our search space to something which is very very close to our first occurrence. So when this ends, you would have exhausted your search space, and when you have exhausted your search space, this is, let's say, your high, this is your low. So always your high would be something here, high would be this and low would be this when you have exhausted your search space. So low would be, let's say, kind of out of your search space, just out of your search space to the right. So this would always store the first occurrence. Got it? If the more traditional way, if you're still confused, what you can do is just whenever your nums of mid is greater than equal to target, what you can do is just assign, let's call it what did we call fpos, right? Fpos equal to mid. So this is the safe way. If you didn't understand the low one, what you can do is the first position equal to mid. You will just keep track of it in separate variable, right? You can do this. But yeah, this is the approach. We found the first index. Let's try to find the last index. Let's erase this. Initialize our search space again. This is our low. This is our high. It would be low would be 0 and high would be 6. Okay. Now let's see how this affects our condition as well. Let's erase all of this. Yeah. So let's take some examples before we actually run our binary search. What would happen? Let's say our mid was this. Then where would I have to search? I have to search right, because my target is 8. I need to search right now. I need something greater than my nums of mid. So I will search right. Okay, fair enough. What if my mid was here? My now a target is equal to nums of mid. Okay, but okay, I agree. This can be last occurrence, but is it? Can I guarantee that is it the last occurrence? I don't think so. What I'll do, okay, I'll appreciate that this might be last occurrence. I would maybe store it, but what I'll do now is search right more. I'm saying, hey, okay, that's okay. You can be last occurrence, but I'm searching right so I can find better, like something more to the right, which is equal to target as well. So what I'll do, let's just save it and I'll search right. Okay. So I'll search right again. What if my mid was this? Again, my mid is equal to target, but we need to search right to find last occurrence. We need to still search right. So I'll still search right. This would be my last. This will be mid. Again, I'm saying we need this is equal to target as well, but we will still search right. Okay. So this is and let's say mid was here, right? Now we are greater than target. Now I'm sure that I need to search left. We have exhausted our right search space, and now we need to search space left. We need to search left because after 10, after nums of mid, everything would be greater than target, with target which is 8. So now I would eliminate the right half and search left. Okay. So let's do it by example so things would be more clear. I was just giving you the intuition. It is very similar to our finding the first occurrence itself. So what did we deduce from our conditions? If my basically if my nums of mid is greater is less than or equal to target, let's say it is less than or equal to target, what would I do? If it was basically 7 or the 8 itself, what did we do? What does our intuition tell? Okay, I have told you that in that case we would just search right. Make sense? And if it was greater, then we would obviously search left. By using these two conditions, let's dry run our binary search now. So this is our low, this is our high, and this would be our mid. Now I can see that my nums of mid is equal to my target, and this condition holds. It is lesser than or equal to my target. So I'm saying, okay, this might be my first occurrence, but still I'll search right. So let's search right by updating our low pointer to be mid plus 1. Low would be here. Let's update our low to be 4, and let's compute mid again. So mid would be this now. So again I'll check, is my nums of mid equal to target or less than target? So it is less than equal to target, right? So I'm saying, okay, this might be my answer because it is equal to target as well. But let's search right once more. So we might find something more to the right. Okay. So let's search right again as this condition holds. Okay, as this holds. Yeah. So to search right, I would update my low pointer to be mid plus 1, which would be 5 plus 1, 6. Right. So this is my low, this is my high. Is my nums of this would be my mid again, right? So this would be my mid itself. So is my nums of mid lesser than equal to target? No, it is now greater than target. Now 10 is basically greater than target, greater than 8. So I need to search left now for sure. So I would just search left now, search left as this condition holds. Got it? So to search left, what would I do? I would do high equal to mid minus 1. So let's do high equal to mid minus 1. Mid was 6, so this would become 5, and high would be here. Yeah, so as you can see now, my high is like now lesser than low, right? So we have exhausted our search space. We now terminate our operations. We have exhausted our search space. So we terminate our binary search here. So now what do you see? What do you observe? Can you observe that my nums of high basically stores the last occurrence? Right? Now nums of high stores the last occurrence because the same reason. Now we have exhausted our search space. If we are trying to optimize to search right, we are very close to our let's say this was last occurrence. We are very close to our last occurrence, but to the right. So when we exhausted our search space, our high pointer would be here and low pointer would be here. Low pointer would be greater than this. So low pointer would lie in the right half of the search space, and high pointer would just point to last occurrence, right? So try to do this on your own. You would get why is high storing my last occurrence and why was low storing my first occurrence. Okay, if you're still unsure, what you can do, whenever you have this condition, nums of mid is less than equal to target, right? Or whenever it is equal to target, what you would do is just store, let's call, or it was lpos, right? So L pos equal to mid. You can just store it and return it. Okay. Yeah, that's it. I think now let's discuss some edge cases and the cases in which the target is not found. What would happen in that? So, or uh, you basically have this observation, right? If at least one number exists, then we would have the first occurrence equal to last occurrence. Let's say we had target equal to 10. So first occurrence, let's call it f pos and l pos. So first occurrence of 10 would be 6 itself at index 6, and last position of target 10 would be 6 as well. So even if we have one element, the first and last position would overlap and it would be the same index. Okay, this is one case. And the second one I want to explain is that if target does not exist, then what? Then we would have to check uh, if target is, let's say, 11, we would have exhausted our search space and our search space would have terminated something like this. This would be my high and this would be my low. Make sense? So I need to now, for finding first occurrence, I would have checked this, whether my low the first occurrence is always in low, right? So whether my low pointer is basically in bounds or not. So if it is in bounds, I would check, is it equal to target or not? If this both conditions hold, then I can say that yeah, now this is my first occurrence. But also for last occurrence, I'll check the same. I have to check whether high is in bounds, and if it is, then I would have to check whether this high is equal to target after my second binary search. Okay, if this both condition hold, then high would store the last occurrence. This low and high would are of different binary search. The binary search, in binary search 1, where we find first occurrence, we would have our answer in low, and in second binary search we would have our answer in high. These are two separate things. Okay, I think let's write the code. The things would be more clear, and I would discuss two approaches of writing this code. So let's get into it. uh, we would have to, as I said, we would have to use two binary searches, right? So let's try to find first occurrence. Yeah, so let's have our f pos, let's call it f pos equal to -1. Initialize our low and high pointers, low pointer to be 0 and I equal to n-1. Let's initialize our mid n as well. N would be just size of our array, and equal to nums dot size minus 1. Yeah, nums dot size. Yeah. So while my low is less than equal to high, that means I'm still in my search space. So I'll calculate my mid equals to low plus high minus low by 2. So now we would, for first occurrence, let's write down our conditions, which was basically if my nums of mid is greater than or equal to target. So I would search left. Because if it is equal to target as well, I'm saying I'll search left to find a better first occurrence, the actual first occurrence. So let's search left. I would search left in this case, which is basically moving my high pointer to be mid -1. Else I can just do low equal to mid +1. If my nums of mid is less than target, I'll just search right. So this would be done. Now our f pos is basically low here, right? And as we discussed, it would answer the first occurrence. If it exists, it is stored in low pointer. We can do another like the safe one as well. I would show that later, but now let's find the last occurrence. So let's reinitialize our pointers, low equal to 0 and high equal to n-1. While low is less than equal to high, what we can do is calculate mid. right? Now the same condition what we discussed, if my nums of mid is, let's say, lesser than equal to target, we line left search space, right? It is lesser, we are at 7, we need to find 8. So what I'll do is now search right. So I'll search right. So to search right, I'll just do low equal to mid plus 1. Else we need to search left, which is just high equal to mid minus 1, as I explained. And our we didn't initialize lpos, right? So our last occurrence, let's initialize it to lpos equal to -1. And after we exhausted our search space, our last position would, our high would store our answer, but let's store that in lpos. We've discussed why high would store. So if now I need to check that my lpos and fpos, the first position and last position, are in bounds and are equal to target. If the both condition hold, then they're applicable to be our answer, right? So let's do it. Let's create a vector and vector of int answer. Let's initialize that to let's have it like this itself. So I'll check the bounds. If my fpos is greater than equal to 0, and then my fpos is less than n minus 1, is less than my n, basically, right? And then nums of fpos is equal to target. So this condition basically checks that my fpos is in bounds of an array and it is equal to target as well. Index represented by it is equal to target. So if this holds, then I can say that my answer, I can just push back answer dot pushback equal to fpos, right? If it does not hold, just push back answer dot pushback -1. And now we can do similarly for lpos. If my lpos is greater than equal to 0 and lpos is less than n, and my nums of lpos is equal to target, then I can just do answer dot pushback lpos. Else if lpos is out of bounds or it is not equal to target, then I can just do answer dot pushback -1, and we can just return answer. So this is our code. This is quite lengthy because we are doing 2 binary search in this function. So let's try to run it. It should run. Let's see if we have any errors. Okay, it is running fine. Let's submit it. Okay, it got accepted. So yeah, that's now if you have a doubt with this, you can just do run and on pen and paper, or you can actually play safe here. If your nums of mid equal to target, let's say we are going towards like first occurrence, right? So closer and closer towards first occurrence. So whenever I find my nums of mid equal to target, just I'll store my fpos to be mid. You can do this as well. This is fine. And yeah, you'll continue your search. You'll still continue your search. You won't return here because we are not just finding the target element, we are finding the first occurrence of it. We need our search to terminate. So let's do it here. Let's remove this and we can do lpos, the same for lpos. If my nums of mid now equal to target, what I'll do is just store lpos equal to mid. So I'm going closer and closer to my last occurrence. So whenever I find my nums of mid equal to target, it might be my last occurrence. So I'm initializing like making this to mid. So we are removing this. So now what we can do, we don't have to like make this checks and all. Then we can simply make our answer to be fpos comma lpos. Why? Because if we don't find the target, or if it is not in bounds, then our lpos would be -1 and fpos is also initialized to -1, so it is automatically -1. So let's try to run it as well. Yeah, let's submit it. Yep, this got accepted as well. So whatever is visible to you, you can use that approach. But this low and high pointer, this is like impressive to him interviewer because you understand the search space now. So try to understand the first approach as well. Now the second thing I want to tell you is that we have one more approach to solve this problem, is using our favorite functions, which are lower bound and upper bound. Can we solve the problem in much less line of code using these functions? You can ask the interviewer itself, are these functions allowed or not? Can I use them? If he says yes, you can just use those functions, but it is highly unlikely. But you should know about these functions. Uh, so let's discuss that as well. So as we know, let's discuss first what does lower bound and upper bound return. So lower bound, let's actually discuss on iPad. So what does my lower bound function return? This is my lower bound, and third argument would be target. This would return me, yes, you guessed it right, first occurrence of target. Even if we have duplicates in our sorted array, still our lower bound will return me the first occurrence at which it finds my target. Okay, and this is important things you should know. The second is for upper bound. Now this won't give me the last occurrence of target. If you're guessing that, it would give me something just greater than target. Greater than target. Okay, so let's try to implement this in code, and let's see how do we handle the edge cases and the cases where we don't have the target as well. So let's write the code. Right. So our first occurrence, let's call it LB low bound. So it would be using a low bound function. Let's pass our beginning and end as our search space, and we'll pass our target as well. Also we would have our upper bound to be a bound, starting of search space, ending of search space as nums of n. We would have our target. So I know for sure that low bound, let's have our vector of end answer as well. I know for sure that my low bound would give me first occurrence. Let's focus on the first occurrence now. So if my LB is not equal to nums of end, and then if I dereference my LB, if it exists, it should be equal to target. Or if target does not exist, then LB would give me something greater than target, which we don't want. So what I'll do is I'll do a LB dereferencing LB, and I'll just check is it equal to target. It should not be equal to nums of n, or I'll be not able to dereference it. This statement won't be executed if this fails right here. So this should not be equal to target, and after dereferencing this pointer, I should get target. So uh, if this holds, basically I'll do answer dot pushback. We don't need this brackets actually, because we are just using one if statement, and if answer dot pushback will pass the index, which would be just lb minus nums dot begin. If you're confused how to use low bound on upper bound, you can just watch the video in description on in the pinned comment. So else if this condition does not hold, what I'll do is just answer dot pushback negative. Now this was for first occurrence, right? This is my first occurrence. Now for last occurrence, for last position, what we can do is do a similar check, but we need to understand that upper bound returns me something greater. So let's take this example itself, the example 1 here. So in this case, if I run the upper bound function for target 8, what would I get in return? This I would get an iterator for this 10, right? So my last occurrence would be index before 10, right? This would be my last occurrence. So to get it, I need to do pointer arithmetic and subtract 1 from our upper bound if we can subtract. But let's say upper bound returns you 5 itself, then you won't be able to subtract, right? So you have to do that one check. So basically, if my upper bound is not equal to nums dot begin, then I can do ub minus minus. I'm going one index before. This is my actual last occurrence and this is my upper bound, so I'll move my upper bound here. So I'll do ub minus minus, and now I'll just check if my uh, dereferenced ub is equal to target. If this holds, then I'll just answer dot we have found our last occurrence, and I'll just push back to ub minus nums dot begin, right? Else we didn't find our answer, we didn't find our last occurrence, so I'll just push back negative 1 and I'll just return answer. So this is, let's run it and check. Okay, we have a runtime error. Interesting. Okay, our nums can be empty as well. Okay, that's interesting. I need to check now. Also, we need to have that check. ub should not be equal to nums.end, right? If this happens, yeah, this is runs fine. So we had to just check whether upper bound is not equal to end, because as we saw this case where array is empty, I didn't expect the array to be empty, to be honest, but yeah, if our array is empty, we need to check whether the upper bound is not equal to end as well after subtract. So yeah, let's run it now. This should now hopefully run fine. Yep, this works. So yeah, that's it from my end. And in this question we have discussed like 3 approaches, like almost 2 approaches to code and 1 modification. So yeah, thanks for watching. Bye.